Hi, today I'm going to be talking to you about scientific math. So, all of the arithmetic is the same regardless of what discipline you're looking at, but in science we have some terms that we use and we have some methods that we use that you may or may not use in your general arithmetic in algebra and geometry. So one of the first things that we see a whole lot of confusion about is a confusion on two terms, accuracy and precision. So accuracy and precision are not the exact same thing. Accuracy and precision are actually very, very different in terms of what they mean. If you have something that you want to be very, very, very good as far as a measurement, you want it to be both. So if you want something to be you have to have something both accurate and precise. So accuracy. Accuracy is simply the ability to get very, very close to the true value, the real value. And if you think about the term accurate or actual and the beginning of accuracy, those two terms look very, very close. So accuracy is great. However, if you take accurate measurements but they aren't precise, you can have that measurement be a little bit over, a little bit under, and not have any good way of knowing exactly where that true value is. Precision is how close, every time you measure, how close can you get to it, the exact same value. It's basically being consistent, being persistent. And so precision lets us, when we have precision tools, they always will measure to the same exact point. Whether or not that point is accurate or not is how quality of a tool you have. And so you want a tool that is both accurate and precise. You don't want to have it be precise but be measuring the wrong value, or be accurate but then get all kinds of different values. You want to, every time you use a tool, every time you take a measurement, for it to be both accurate and precise. One of the other things that we are going to talk about is the metric system. So you will be doing a foldable to help you with this. But going through, when we talk about the metric system, it is an international system of units. There's two countries in the world that don't use the metric system. It's Guam and the United States. Everywhere else uses metric. So with the metric system, the system isn't that old. It is a fairly new system. It was developed in the late 70s, early 80s, and adopted. And basically, scientists and business people all around the world got together and said, we need some kind of standard units. We need standard measurements because they're not standard. And they based the metric system on things that you can actually recreate anywhere. So for example, all of the metric system is based on water. And when we go through, a milliliter is 10 drops of water. And the weight of those 10 drops of water is a gram. And if you have a 1,000 liters cubed, then, so if you have a milliliter and you cube it, it is a millimeter. So if you have the kiloliter cubed, you actually end up with a meter. So what this means is, as long as you have water, you can come up with the mass, the volume, and the distance that is the same anywhere you go. That's different from American Standard. In American Standard, we actually have the pound, and it is a singular thing. It is one weight that's up at the Standards and Technology, the National Standards and Technology up in Gaithersburg. There's actually a pound that's 1 pound, and everything else has to be compared to that. And so in order to say something's a pound, it has to go up to NIST. Alright, so our meter, our prefix there is a lowercase m, liter, uppercase L, grams, lowercase g. Now, Then we have some standard prefixes for the metric system. And what all of these leaders of technology and science decided is we're going to do everything on a base of 10. That way we don't have to change any values. We don't have to do arithmetic to change our units. We just have to move the decimal point. Makes life a lot easier. Now, as to why the United States doesn't use the metric system, primarily it's hubris. We didn't come up with the idea all on our own, so we're going to stick with our own system because we're very, very proud and we didn't come up with the idea. That's the best answer I have for that. But everywhere else in the world uses the metric system. Alright, our standard prefixes, some of them are ones that you use all the time. Some of them we don't use quite as often. There are standard prefixes that go way up and way down, but the ones that we concern ourselves in biology just go to 1,000 times more or 1/1000th of a value. So we start with our base unit, okay, and we're going to do these as exponents here. So 10 to the 0, or a base unit of 1, is our meters, liters, and grams. So now let's first go small. If we get smaller, we then go to a deci. So you can have a decimeter, a deciliter, or a decigram. That's 1/10, or 10 to the -1 power of a value. Then we go to one that we should be fairly familiar with here, which is centi. Centi is 1/100th. Okay, we see centi primarily with centimeters. However, you can have centiliters and centigrams. And that would be 10 to the -2. And then finally our milli. And with milli, it's 1/1000th, and it's 10 to the -3. We should be familiar that in order to get these decimal points, we use a negative exponent there. Now, if we're going to go bigger, and our prefixes here. So deci, our prefix is a lowercase d, centi, lowercase c, milli, lowercase m. And we simply put these prefix abbreviations in front of the abbreviation for the base unit to give us our full value. Going bigger. Deca. Deca is 10. So 10 times bigger, or 10 to the 1st power. That prefix is dA. So for a decameter, it would be DAM. The next one would be hecto. Hecto is 100 times bigger, or 10 to the 2nd. And then finally, kilo, which we often see with kilograms. Kilo is 1,000 times, and that's 10 to the 3rd power. So this is where all of our standard prefixes is the primary ones that we are going to be doing. Alright, so the next topic that we want to talk about is how do we do conversion. So really it's moving the decimal point, and that's all we have to do because everything's a base of 10 and our number system is a base 10 number system. So the first thing you want to do is you figure out where's your start point. Your start point is wherever your decimal is for the number right now. And we take that start point, and then if our start point, for example, if we're starting at hectometers, so we look at what our unit is, and that's our start point. And let's say we wanted to go from hectometers to centimeters. We count the number of jumps. So if we go from hectometers, we go 1, 2, 3, 4 jumps. And with those 4 jumps, so now we have 4 jumps. Then what we'll do is we'll move the decimal point 1, 2, 3, 4 times, and since those jumps were going to the right, we'll move the decimal point 4 places to the right. And then we will have the value that gives us the number of centimeters. Pretty simple. If we go the other direction, let's say we wanted to go from grams to kilograms. We would go and count. We'd say, okay, we started here. We went 1, 2, 3. So we would then move our decimal point 3 places to the left in order to give us the value for our kilogram. Now, with this, alright, so since we're dealing with these and you start moving and we add a lot of zeros either in front of or after when we do these conversions, one of the things that we often do is we put our numbers into scientific notation. So what scientific notation does is it lets us very easily compare really big numbers and really little numbers without having all the extra zeros. It's hard to see when you have 10, 20, 30 zeros in a row which number, whether or not it was 10 zeros there or 11 zeros. It becomes very hard to immediately tell which number is bigger. So what we do is we actually go into scientific notation. So scientific notation basically lets us write these really big numbers or really small numbers and compare them very easily. So in the format, what we always have is we have a number between 1 and 10. Okay, so no values that are decimals, no values that are two-digit numbers. It's a single-digit value with a decimal point, and then it can have some additional values in a decimal, and then we multiply it times 10 to an exponent. So, for example, if I have this number 350,000,000,000,000, decimal point 00, what I would then need to do is I need to move my decimal point. And so I'd take my decimal point and I would see how many jumps do I have. So I'd start with my decimal point here and I would jump and I would go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times I would have to move the decimal in order to get it so that there was only one digit in front. So then what I would write down is I would have that 3, I moved my decimal point to here, so 3.5, and then times 10. Now I moved my decimal point to the left. Okay, I had started with a really big number, a positive, huge number, a whole number bigger than 1. So I'm going to have a positive exponent. Now if I had started with a decimal, so let's say I took this number here and I flipped it around, and so it was decimal point 0.000000000035, then I would end up putting a negative there if it was a large decimal. But it wasn't. It was a positive whole number, so we're going to do a positive 11. So this would be the value for the scientific notation. Okay, so hopefully this makes sense. We will have some more practice with scientific notation next class period. So today you should be doing your metric conversions is the primary focus today. Thank you.